Welcome to our guide on drone perception systems. Perception is key to how drones understand and interact with their environment. A drone's perception system consists of a variety of sensors, and which ones you choose depends on what you want the drone to achieve. At the most basic level, drones need an IMU, an inertial measurement unit. The IMU tracks the drone's acceleration and orientation, ensuring stable flight. Then we add a camera, usually for basic visual input, and a GNSS module, which helps the drone understand its global position using GPS or other satellite systems. With just these three components, your drone can fly stably, track its position globally, and capture visual data. This setup is sufficient for basic flight and image capture. It's ideal for simple tasks like photography, basic mapping, or autonomous flight in areas with strong satellite signals. But what if your drone needs to navigate more autonomously, or map 3D environments? That's where stereo depth cameras come into play. These cameras can measure depth and create a 3D map of the environment, allowing the drone to detect and avoid obstacles. In fact, depth cameras are a great addition for applications like indoor navigation, obstacle avoidance, and localization in places where GNSS signals may be weak or unavailable. Next, consider adding an RGB camera. With RGB, your drone can see the world in color and texture. It can be used for object detection, scene understanding, and even semantic mapping, where the drone classifies objects in its environment. When combined with depth sensing, the drone becomes more intelligent, capable of understanding the world in 3D, just like we do. Now let's take it up a notch. In more demanding applications, such as detailed 3D mapping, topographic surveys, or forestry analysis, you'll want to add LiDAR. LiDAR, light detection and ranging, is a sensor that uses laser pulses to measure distances, generating highly detailed point clouds. It's incredibly useful for accurate terrain mapping, vegetation scanning, and when you need extremely precise depth data in more challenging environments, such as forests, caves, or complex urban settings. LiDAR is invaluable for applications that demand high precision, but it's also more expensive and power-hungry than simpler sensors like cameras, so it's typically added only when detailed mapping and accuracy are essential. For even more robust capabilities, drones can integrate additional sensors like radar, ultrasonic sensors, and thermal cameras. These sensors allow drones to function in low-visibility environments, such as during night flights or in harsh weather. Combined with LiDAR, these additional sensors can help the drone navigate with high redundancy, ensuring safe operations even in complex and cluttered environments. Another key sensor to mention is RTK GNSS. This is a high-precision positioning system that provides centimeter-level accuracy. It's especially useful for applications that require survey-grade precision, such as land surveying and agriculture monitoring, where small errors can lead to significant mistakes. RTK GNSS improves the global positioning system's accuracy by correcting errors using a local base station. Finally, let's talk about the AI-powered integration. Modern drones don't just rely on their hardware to navigate. They integrate artificial intelligence to analyze sensor data in real time. AI enables drones to make decisions based on sensor inputs, optimize flight paths, detect objects in complex environments, and even learn from past flights. The AI can run on board, processing data from cameras, IMUs, LiDAR, and more, allowing the drone to react autonomously. So what can you achieve with just stereo depth cameras, RGB, GNSS, and an IMU? Basic flight and navigation with GNSS, obstacle detection and avoidance using the stereo depth camera, basic 3D mapping and localization, real-time analysis and object detection using RGB cameras. But when you add components like LiDAR, RTK GNSS, thermal sensors, and AI, you unlock more advanced capabilities like precise 3D mapping, high-accuracy surveying, complex path planning, and even AI-driven autonomous exploration. To summarize, a drone's perception system is a powerful combination of sensors and algorithms. The system you choose depends entirely on the tasks at hand, from simple photography to complex surveying or autonomous navigation. By integrating the right sensors, drones can become truly intelligent and versatile tools for a wide range of applications. When designing a drone, the perception system directly impacts the choice of MCU, microcontroller unit, as well as the power consumption and weight of the overall system. Let's explore how these factors are interrelated. First, the MCU is the heart of the drone's computing. It processes sensor data and executes algorithms that enable the drone to navigate autonomously. When you add complex sensors like LiDAR, stereo cameras, or high-precision GNSS, the computational demands on the MCU increase significantly. A drone's MCU must be able to handle multiple sensors simultaneously while maintaining real-time performance. For lighter applications, a low-power MCU might suffice, but as you add LiDAR, AI models, or real-time image processing, a more powerful MCU is needed to keep up with the data throughput. MCU suggestions for different applications. For low-power, basic applications, with minimal sensors like RGB camera, IMU, GNSS, STM32, e.g. STM32F4 or STM32H7 series. Power consumption. Low, 1 watt. Efficient processing for basic sensor fusion, flight control, and communication. Use case, ideal for drones with light payloads and basic tasks, e.g. photography, simple navigation. For moderate power sensor-rich drones, adding cameras, stereo, light LiDAR, and GNSS. NVIDIA Jetson Nano or Jetson Xavier NX. Power consumption, 5 watt Nano to 15 watt Xavier NX. Features: great for image processing, AI, and sensor fusion. IMU plus depth camera plus GNSS. Use case: perfect for drones requiring onboard AI processing, object detection, and obstacle avoidance with moderate payloads. For high-powered complex applications, with high-end LiDAR, RTK GNSS, AI models, NVIDIA Jetson AGX Xavier or NVIDIA Jetson Orin NX. Power consumption: 30 watt to 60 watt AGX Xavier, 15 watt Orin NX. Features high computational power with AI support. Perfect for drones requiring real-time mapping, high-precision flight, and advanced AI tasks, e.g. SLAM, path planning. Use case: heavy-duty drones for industrial, surveying, or autonomous delivery tasks. Power consumption is one of the biggest challenges when adding more sensors. Each sensor comes with its own power demands, and high-precision sensors like LiDAR or high-res cameras can consume significant amounts of energy. For instance, a LiDAR sensor can draw anywhere from 10 watt to 40 watt, whereas cameras might consume around 2 watt to 10 watt, depending on their resolution and processing. If you're running AI models on board, that could push power usage to even higher levels. Weight is a critical factor too. Every additional sensor adds weight, which directly impacts flight time and stability. LiDAR units, GNSS modules, and cameras can all add significant weight. For example, LiDAR might weigh 200 g to 2 kilograms depending on its type. And RTK GNSS systems typically add 100 g to 500 g. With that in mind, you'll need to select an MCU that not only supports the required processing, but is also lightweight enough to maintain flight efficiency. This balance is crucial for small UAVs or compact drones, where weight directly influences performance. In summary, when selecting the MCU, power consumption and weight must all be considered in conjunction with the perception system's requirements. The more sensors you add, the greater the computational demand and power consumption. With the right balance between MCU processing power and weight, your drone can achieve high autonomy without sacrificing flight time or stability.